Hello, my name is Kyla Fallis from Bath High School, Lima, Ohio. I'm presenting a novel approach to bioelectrogenesis by utilizing microbial fuel cells as a sustainable energy solution. My research directly addresses two of the most pressing environmental challenges that we face today, both climate change and organic waste mismanagement. Each year, the average American generates approximately 219 pounds of food waste, contributing to a national total of 103 million tons of organic waste annually. When this waste goes to landfills to decompose, it releases methane, a greenhouse gas 25 times more potent than carbon dioxide. In total, decomposing organic waste accounts for around 15% of our global methane emissions, and in the US alone, results in about 9 million pounds of CO2 equivalent emissions every year, or about 10% of our total emissions footprint. But a lot of people don't actually understand how this gas in the air translates to the proverbial end of the world that we hear about on the news. The best way to think about this process is like a blanket. Greenhouse gases reflects the sun's rays back at the earth again and again, just like a blanket reflects body heat. The thicker the blanket, the more heat's going to get reflected, and unfortunately, we've been adding layers to the blanket around the earth for about 200 years. We've already seen some of the impacts: stronger storms, rising sea levels, and an increase in the ocean's pH, and the ecosystems around us struggling to keep up. Scientists have concurred that we're already in the middle of the sixth mass extinction, partially because the species around us can't adapt fast enough. Given these statistics, it is imperative that we develop waste to energy conversion technologies that not only are able to mitigate greenhouse gas emissions, but also provide renewable energy solutions. This is where the microbial fuel cell comes into play. Microbial fuel cells are able to leverage the metabolic pathways of electrogenic bacteria to oxidize organic substrates, transferring electrons through an external circuit to create an electrical current. The key biological catalysts that I found present in my system were Geobacter sulfurreducens and Schoenella onidensis. Both of these exhibit extracellular electron transfer via conductive pili and cytochromes embedded within their external membranes. To simplify this just a little bit, we're going to compare the microbial fuel cell to something we should all be very familiar with: the human body. When you or I eat food, we're able to turn that into energy because a number of bacteria within us breaks down those organic molecules. Simply put, the same exact thing is happening within a microbial fuel cell, but instead we're able to turn that energy into an electrical current. Moving on to my actual project, to explore the feasibilities of microbial fuel cells as a renewable energy source, I constructed my own system using compost as a bioactive fuel source. Seen here, the system consists of an anode chamber where our compost would be, and the anaerobic bacteria are facilitating oxidation reactions and then releasing electrons, and then our cathode chamber, which would be filled with water, is exposed to oxygen and serves as our final electron acceptor. These chambers are connected by a proton exchange membrane to allow ion exchange and maintain charge neutrality. So within the system, all the reactions are happening in here. Our permeable exchange membrane, protons can pass through, but electrons can't, so they're stuck in this side. This means we have a lot of electrons getting very angry and stuck in this container without any way to leave. To solve this, we input an electrode into both containers, making the electrons take the long way around to reunite with their positive counterparts by creating an electrical current. Now, up to this point, my project has been done before. Microbial fuel cells are a lot less popular than something like windmills, but have been utilized to produce electricity. However, in all my research, I was unable to find a study done using household waste or compost. Simply put, this technology generates very little energy, so it just isn't seen as a viable alternative for energy production. My goal for the rest of my research was to change that. In my initial trial, the system produced about 0.88 volts and 22 milliamps, resulting in 19.4 milliwatts of power output. By making a few changes moving into my second round of testing, I conducted a comparative analysis of electrode materials and found that carbon cloth electrodes exhibited about a 42% increase in electrical output due to superior conductivity and microbial adhesion properties. Additionally, I reduced the electrode space from 5 to 3 to 1 centimeters, and this increased the voltage by about 12%, improving ion diffusion kinetics and decreasing internal resistance. Additionally, increasing the size of the container to 2 liters also optimized my energy production. With these changes, I was able to achieve an increase in voltage to 1.36 volts and 127.24 milliamps, representing about a 54% enhancement in power density. Additionally, I evaluated compost at various decomposition stages to determine my optimal substrate efficiency. Compost aged 12 to 18 months yielded about 63% higher voltage output compared to fresh compost, which did exhibit a stronger initial output but declined rapidly due to volatile fatty acid accumulation. Compost that was over 2 years old demonstrated reduced metabolic activity and lower energy output overall. Now, to translate all this technology and numbers into a tangible application, I designed and 3D printed the first of its kind, the Leica lamp. This is a fully functioning lighting system powered entirely by microbial fuel cell technology. This system consists of the electrode materials used in test 2, my anode chamber, which has compartments to optimize electrical output in the cathode chamber, which would be filled with water, and also an integrated DC step-up converter, which improved overall energy efficiency by 48%. I also incorporated a battery storage system, so that all of the electricity produced could be stored and utilized effectively. The Leica lamp achieved a total energy output of about 925 watt-hours in a week. This means that using my system, the lamp would produce energy and store it for about 11 hours, and then be able to produce light for around 2.5 hours. The total cost of an individual Leica lamp comes out to around $16.77. This innovation has substantial potential for any off-grid energy applications, particularly in the regions where over 770 million people currently lack access to affordable electricity. In addition to lab testing, I also conducted widespread surveys to assess household composting habits, potential adoption rates, and cost-saving implications of microbial fuel cell technology. Based on my findings, the average U.S. household discards enough food waste to generate the electricity capable of powering 5.7 Leica lamps daily. This would provide them with about 13.47 hours of light in a day. If implemented, a microbial fuel cell system could save a household up to $128.13 a year in electricity costs. Additionally, my data indicated that over 60% of respondents expressed interest in sustainable energy solutions if cost-effective, reinforcing the viability of the Leica lamp for mainstream adoption. Now, scaling this technology up could yield even more significant environmental and economic benefits. If only 1/3 of the households in the U.S. alone integrated an MFC system, it would generate 105 million kilowatt-hours annually, save $1.8 billion in electricity costs nationwide, offset about 10 to 20% of landfill facility energy use, reduce wastewater chemical oxygen demand by as much as 75%, and completely replace kerosene lamps, which contribute to around 190 million metric tons of CO2 emissions annually. Beyond electricity generation, microbial fuel cells using urea-rich manure as a fuel source would be able to reduce nutrient runoff by as much as 60%. This is particularly crucial in presenting dead zones, such as the massive hypoxic region in the Gulf of Mexico. While microbial fuel cells might not yet be efficient enough to replace large-scale traditional power sources, continued research in bioelectrochemical optimization could significantly enhance their performance. My future work with this project is going to focus on optimizing microbial consortia selection to increase electron yield, enhancing my proton exchange membrane efficiency to reduce resistance, improving my electrode surface modifications in order to maximize biofilm formation. By harnessing the metabolic capabilities of electroactive microorganisms, MFCs present a unique opportunity to bridge the gap between waste mitigation and sustainable energy production, focusing on a decentralized energy system. The potential to convert organic waste into electricity on both the small and large scales could contribute to a more decentralized, renewable energy infrastructure. If you have any questions, feel free to check out the rest of my project on my board.